Hi, in this video, we're going to take a look at non-parametric tests for the purpose of experimental analysis. Okay, so in a parametric test, I have assumptions about my data that need to be true for me able to come up with the right conclusion based off of the results I'm going to get. If those assumptions are not met, I can't trust the results from my parametric test. Okay, well, I get paid to reach conclusions. I get paid to give information about data. I look at my data. I say, hey, the assumptions aren't met. I still need to deliver. I need to come up with an answer to my stakeholders, or I'm not going to have a job for very long. So I need to do hypothesis testing. But clearly, when I look at my data, I can't trust the hypothesis test I want to do. Well, what do we do? Well, instead of doing a parametric test, which is usually what we typically talk about when we do hypothesis testing, I'm going to do a non-parametric test. So when I say non-parametric test, that is going to be a lower level of assumptions, like fewer assumptions, less stringent assumptions on our data that are needed for us to reach the correct conclusion when we run our hypothesis test. Now, when I say parametric and non-parametric, it's actually a gray scale. That parametric test is going to have more assumptions, more things need to be satisfied, while non-parametric tests are going to be a little bit more general and won't require as much to be met. All right, so you would naturally go, well, why would I even bother with a parametric test if non-parametric tests don't require so much, assumptions, right? When you assume you make an ass out of you and me, I've got assumptions, there's more opportunity for me to make a mistake on my assumptions with a parametric test. Well, unfortunately, it's going to work out that parametric tests, the ones with more assumptions, are more likely to reject the null hypothesis when the null hypothesis is incorrect. So parametric tests overall in general have more power than non-parametric tests. So it's a trade-off. With parametric tests, I have more power and the shortcoming of more assumptions. With non-parametric tests, I have a shortcoming of less power, but I have the advantage, I have less assumptions. And so we have to make a decision on which one we want to use. Now, something that's also really cool about non-parametric tests is that if I needed to, I could do a lot of them by hand. Believe it or not, with not too large of a data set, I could actually pencil and paper do non-parametric tests manually by hand for a lot of them. As long as I can identify like the order of my data and rank order that is, a lot of times we can actually perform non-parametric tests if I had to. So if I was stranded on a desert island where I have pencil and paper and no computer, no calculator, and I needed to do statistics to get off that island, I would be doing non-parametric tests. Okay, so one of the biggest complaints I have about this topic is that we don't really set up like a table for at least what I've seen when I look at textbooks, is that we never really just say, hey, if this test isn't working, bounce to this non-parametric one. This parametric test, the assumptions aren't met, bounce to this non-parametric test. So here I've gone through and I created a table for exactly that purpose. Now, I'm not going to go through all of the details of all of these. On the far left-hand column, I set it up as we have the goal of the hypothesis test here. Then we have the parametric tests that we typically use. You'll notice that many of these appear in your introductory and elementary statistics courses. And so these are the ones that we use most often, that we lean on the most, as long as their assumptions are met. Remember, anytime I'm doing one of these tests, I need to have the assumptions met for my conclusions to be worthy of believing. Okay, so here's the parametric tests that I would use. And then here is the Python package that I could go to, or the Python code that I could go to execute. Now, over here, if this is my goal, but my assumptions aren't met for the parametric test, I bounce over to the non-parametric test over here. And here's the function in Python that I can use for this. All right, so if I have a one sample central tendency, well, that's going to be the one sample t-test most of the time. But if I want The non-parametric version, that's going to be Wilcoxon-Stein rank test. Okay. Two sample central tendency. So when I say central tendency, most of the time that's going to be the mean. So one sample central tendency, I'm going to be checking to see, does it look like the mean is equal to something or greater than something, less than something? With two samples, I'm going to be central tendency. Typically, I'm going to be looking at the mean. Are the two means equal to each other, or is one greater than the other, is one less than the other? And once again, I'm going to be using a t-test, but now it's going to be a two-sample t-test. If I'm doing non-parametric, it's going to be the Mann-Whitney U-test, which is the Wilcoxon rank sum test by another name. Now we can also have a paired two-sample central tendency, so that's a paired t-test. Well, now this is the Wilcoxon-Stein rank test also. Now multiple central tendencies. Normally we're going to be doing one-way ANOVA as long as the constant variance and normally distributed aspect is met. But if it's not met, I could bounce to Kruskal-Wallis. Nice. If I have a two-way analysis of central tendency, I could definitely use ANOVA on that. But if the assumptions of ANOVA aren't met for two-way ANOVA, I can go to the Friedman test. Easy peasy lemon squeezy. Now, for one sample dispersion, I wasn't able to come up with a non-parametric one. I looked around a little bit, but one sample dispersion, in parametric, we're going to use a chi-square distribution test. For two sample dispersion, what we could do is do an F test for that. That requires assumption of normality. And under the hood, ANOVA actually uses an F test. We usually don't talk about that test as much, but it's a tool on our tool belt. Now, if I need a two sample dispersion, so in a two sample dispersion, I'm checking to see, do I have equal variance, equal dispersion of two samples, or is one greater than the other, is one less than the other? And that for non-parametric will be Levine's test or Bartlett's test. Now, for goodness of fit test, now the chi-square test is going to be my parametric test that we're saying that it's a chi-square test. We know this coming from like tables of values. There are assumptions involved in that. This one's kind of a weak assumption, but there's a specific distribution to it, so there's assumption going on. We also use Kolmogorov's Smirnov test, which we would use for like two like numeric or continuous values distributions. Independence between variables, we use Pearson's correlation, which has a hypothesis test to it. If I don't trust the linearity assumption of Pearson's correlation, I could use Spearman's rank correlation or Kendall's tau. I like using Spearman's rank correlation myself when I'm doing my predictive analytics. Now, we could have proportions of categorical data, and so we could use a z-test for proportions or a chi-square test, and we can also use Fisher's exact test for a non-parametric version. And then when we get into a survival analysis, my parametric version is the Cox proportional hazards model, or I could use log rank test also. Just to reiterate, we prefer the parametric version of tests because they have greater power if it's appropriate for my situation. If I have reason to believe that my assumptions of the test are met, then I want to use the parametric version. And each individual test is going to have different assumptions. I need to go in and check to see what are the assumptions. Does my data jive with them? If they jive, I use the parametric version. If I look at my data, I look at my situation, subject matter knowledge, and I conclude that my situation, my data, doesn't jive with the assumptions, I bounce to a non-parametric test. All right, so when to use a non-parametric test? So first and foremost, the assumptions are not met. All right, the data is on ordinal or non-normal scale. Which really kind of overlaps with the assumptions aspect. Also, maybe I'm in a situation where I need robustness to outliers. I see that I've got outliers. Maybe I don't have very much data, and throwing out outliers could throw the data off the results because I have such little data, or I'm in the situation where the choice to remove data points could cause a problem. So imagine that I'm going to be under legal scrutiny of my choices of what I do. So let's say we're doing something that involves like human resources, and a labor union could potentially, file a lawsuit against the conclusions of my modeling. And believe it or not, I've been in this exact position. Um, my work has never made it to court. We've always been able to resolve it before that point, because I've been very cautious and very methodical in my work and documentation. But you could see that if I had outliers in my data and I went in and I removed data points because they were outliers, a lawyer could say, well, he's cherry picking the data, he's getting rid of stuff. My client was damaged based off of the conclusions from his analysis, right? So I don't want to be in that position. So if I have such little data that I can't remove outliers, or I can't remove outliers because of stakeholders, I can't remove outliers because of a legal situation or any other situation that I could possibly imagine, I might need to do non-parametric tests just because there's issues otherwise. All right. So, probably the two most common tests to be talked about are going to be Mann-Whitney U tests comparing two independent groups, and Kruskal-Wallis test for comparing more than two groups. And in general, non-parametric tests will be more prone to fail to reject the null hypothesis than their parametric counterparts. They have less power. When when a parametric test is correctly used, it uses the assumed distribution to provide a better hypothesis testing and to have greater power. Using a parametric test when assumptions are not met I can't trust the results. Right? If my assumptions are not met, that I'm doing a garbage in, garbage out, it's random chance from my point of view if I'm going to get the actual correct conclusions. All right, it is almost never wrong to use a non-parametric test, but I will lose power that I would have had if I could have correctly used a parametric test. So, it's just something to think about. All right, so let's generate some fake data involving mineral hardness and rock porosity. And so here is my fake data. I've got sample ID, I've got a rock type, I have location, mineral hardness, and rock porosity, 600 rows of data. All right, so something I always want to do in all situations is that I want to do visualizations that convince people of the conclusions that I'm going to reach. Okay, and so if I'm interested in different distributions, or possibly different distributions or different means, different variations, I can use histograms, box plots, violin plots, box-in plots. There's a wide range of tools at my disposal. And so here I'm going to go over violin plots. So what a violin plot does is that it does the empirical density estimate and then reflects it over a vertical line so that I can see visually what is the distribution of the data. So the curve here on that left-hand side, if I took the violin plot and rotated 90 degrees clockwise, then what would happen is the top half after rotating 90 degrees would look like the empirical density estimate. And so this gives me a way of judging the distributions. Now, you'll notice that on the inside, I have a box and whiskers from a box plot. And that's how Seaborn does this very nicely for us. And so I can visually check to see what is the central tendency of the median, what is the spread coming from the box plot or the violin plot. And I can get an idea of skewness very nicely from this. Now, box-in plots, this is a generalization of the box plot. All right, box plots, first and foremost, don't show them to your stakeholders. And I'll say don't show violin plots, don't show box-in plots to your stakeholders most of the time. If you need to be able to compare things, use regular bar plots for most of your stakeholders. But when you're talking to a data savvy group, like if I'm your stakeholder, you can do more stuff. Let's do something crazy. Let's do something fun. instead of doing regular old bar plots all the time. That's kind of vanilla, kind of boring. All right, so with a boxing plot, what we're going to do, I'm going to do a box plot. Now, inside a regular box plot, I've got that middle 50%. Those two sides of that middle 50% each have 25%. Okay, what I'm going to do, I'm going to create a shorter box on each side that has half of what its predecessor box has. So in the middle, I've got two boxes, each with 25% of the data. Okay, so this has 25%, this has 25%. I'm going to create two new smaller boxes. So previously each one had a fourth. Now each of these represents an eighth of the data. And then I'm going to make another box that has each has a 16th of the data, 1/32 of the data, and so on until I reach some stopping criteria. And then I'm going to have my outliers on the outside. And so this gives a more precise representation of the distribution. The problem with this is that this is a lot going on in one plot. Visually, I think they give a good impression of what's going on. But if I want to be able to actually interpret the parts of the plot, we have a fourth, we have an eighth, we have a 16th. It gets kind of nuanced and gets kind of ugly for that purpose. Box plots do better with like small data sets. If I have a smaller data set, I will choose a box plot over a box-in plot. But when I have a ton of data, then, let's say more than 10,000 data points, you know what? The box plot really isn't using the full power of the data. And so let's go ahead and use that box and plot to get more information out of it. Now, originally these were called letter value plots. They contain more information in the tails. They call the cutoffs the letter values, but only to the depth where the letter values are reliable estimates. And so that's something that's very nice about this is that in the boxing plot, it's going to keep on creating smaller and smaller boxes as long as we have reliable estimates of the ordinal results or the ordered statistics. Outliers are labeled as those beyond the most extreme letter values that we can have. And that's going to be a different criteria. There's, I believe, 4 different ways to identify outliers, but I'm not going to go over that here. All features shown on the letter value plots are actual observations, thus remain faithful to the principles that govern by Tukey's original box plot. Classic box plots have too many outliers and don't show as much information about the distribution. Now, this isn't really a problem when I have very little data because I don't have that much information about the distribution anyway. But when I've got over 10,000 data points, my box plot doesn't take full advantage of the situation. Remember, a box plot is a 5-number summary of my data: minimum and maximum, median, and then first quartile and third quartile. Now, box and plots start with the median and the first quartile and the third quartile, and then go out from there, cutting the amount of data in, represented by a box in half each step of the way. All right, so let's take a look at what it actually looks like. All right, so here's the box and plot. Let's look at the middle one. All right, so here is the regular box that I would get if I had a box plot. So this part stays the same. The darkest box, which in Seaborn, one thing that's nice is that they make the boxes lighter color as you get smaller and smaller proportion of the data to help us visually interpret things correctly. So the darkest part corresponds to a regular box plot, middle box. So I can see the first quartile, the median, and the third quartile. Now, this box here, from the median to the third quartile, has a fourth of the data. This next box represents an eighth of the data. This next represents a 16th, and then next one is 1/32 of the data. And so we get an idea of what the distribution actually will look like in a more precise manner. Now, there's more going on here. And so I personally would not show these to stakeholders. I recommend not showing box plots to stakeholders, even though it's only a 5-number summary. For some people, for some reason, people lock up. I don't know why. All right, so now let's go ahead and apply a non-parametric test. And so here I'm going to use SciPy stats. I'm pulling in Whitney U, and I've got mineral hardness of these two different types of rocks. And I just want to check, are these the same? Yes or no? Okay, so I'm testing to see, do I have the same mineral hardness of two different types of rocks that I have in my sample? When I get a small p-value, I reject the null hypothesis. I conclude that they have different hardness. Now, it doesn't tell me which one's harder, which one's softer. I just know that there's a difference. Now, if I want to be able to check all three groups, so for the different types of rock that I have, we've got three different types. I can't do Mann-Whitney U. Mann-Whitney U is only for two subgroups. If I want to do three, then we're going to be bouncing over to Kruskal-Wallis. And once again, I'm pulling from SciPy. And we can see that we are very, very confident that there's a difference. Notice, just like with ANOVA, this doesn't tell me where is the difference. It doesn't tell me which two are different. Just that somewhere, two groups are different. I don't know which ones those are. I have to go deeper using like Wilcoxon sign rank test. All right, and so then I'm going to do my post hoc analysis, and I want to test for each of these. So, now I'm, going to go in and go through all the different pairings. So I've got mesomorphic and, this pair, and, I can see that I've got small p-values every single time. And so I can conclude after I take in consideration my collection of tests, with a Bonferroni correction or a home correction or something like that, I can reach a final conclusion about what the differences are. I don't want to use my raw p-values because of the possibility that if I'm doing multiple tests, I have more opportunity for a type 1 error. So in this scenario, so really, for what we were doing, if I was checking for the three, I would have done Kruskal-Wallis. Then I would have done these three tests. So I've done 4 tests total. And so depending on how you choose to make your adjustment, either I could do a Bonferroni correction, or which would be just overall alpha divided by 4, or I could use some other correction technique, which I showed elsewhere in another lecture. All right, so that's all I've got for you. Life is short. Do math.